Hello everyone, welcome back to our channel Euclid Mathematics. This is our second video on complex analysis. Now, today we are going to learn singularity and classification using some of the examples from CSIR Net and GATE. Our today's lecture is based on singularity like removable singularity, poles, isolated, non-isolated singularity and branch point. So let's get started. Now here our example number first, which asked in CSIR Net December 2013, which for 4.75 marks. That means multiple answer question. And similar question, same question asked in GATE 2019. So our example is here, f of z which is equal to z minus 1 upon exponential of 2 pi I upon z minus 1. And option is given, f has an isolated singularity at z0 is equal to 0, f has removable singularity at z which is equal to 1, f has infinitely many poles, and fourth option, each pole of f has of order 1. So here f of z is given in our example, which is z minus 1 upon exponential of 2 pi I by z minus 1. So our first option, f has isolated singularity at z which is equal to 0. Okay, so here we have to check which singularity exists in f of z. That is, we will check for pole, removable singularity, branch point, or isolated or non-isolated essential singularity. Now first let's check for the pole. Now we know that the poles which coming from only the denominator. When we substitute denominator 0 for our function, then we get the pole of our function. Now put the denominator 0, that means exponential of 2 pi I divided by z minus 1 which is equal to 0. So substitute denominator 0, then we get the pole of our function. So we can solve it further. So exponential of 2 pi I divided by 0 which is equal to 1. So we need to solve it further. So 1 can be written as e raised to 2n pi I. Why? Because of that e raised to 2n pi I, which can be written cos 2n pi plus I sin 2n pi. Okay, so we know that sin 2n pi which is 0 and cos 2n pi it is always 1. So e raised to 2n pi I which is a 1. So substitute this value here. So e raised to 2 pi I divided by z which is equal to e raised to 2n pi I. So apply log both sides. So it remain only 2 pi I denominator z which is equal to 2n pi I. So cancel similar term from both sides. 2 pi I get cancelled with 2 pi I. So 1 upon z which is equal to n, or n which is equal to 1 upon z. So it seems that z which is equal to 0, which gives function tends to infinity. So here n which is equal to 1 upon z, when we put z which is equal to 0, function tends to infinity. So f has non-isolated singularity. That means we got f has non-isolated singularity because function not defined at point z which is equal to 0. That means our option it is here, f has isolated singularity at z which is equal to 0. We can use other way to solve this option. We know the one standard result. If g of z has pole at z0, then e raised to g of z has essential singularity at z0. So use this result in our example. That is 2 pi I divided by z has pole at z0, which implies e raised to 2 pi I by z has essential singularity at z0. So we know that z0 which is equal to 0, which is the only pole here at z0. Okay, so this implies e raised to 2 pi I upon z, which has essential singularity at z which is equal to 0. By using this short result, we found that e raised to 2 pi I by z has a essential singularity at z which is equal to 0. And we know that limit point of a pole is non-isolated essential singularity. So which gives f has an non-isolated essential singularity, but option A says that f has isolated essential singularity at z which is equal to 0. So option A is wrong. Now in our second option, we have to check f has removable singularity at z which is equal to 1. For removable singularity, we have to apply one short trick here, and that is if function gives 0 by 0 form. Function gives 0 by 0 form, and then we have to apply L'Hospital rule. Okay, so we have to apply here L'Hospital rule, and after L'Hospital rule, if function gives finite value. After L'Hospital rule, if function gives finite value, that means there exists an removable singularity. So let's check for the removable singularity for z which is equal to 1. That means limit as z tends to 1 f of z. Okay, now put the value for f of z, limit as z tends to 1 and f of z it is here. Now substitute z which is equal to 1. We can see here if z is equal to 1 goes to 0, that means 1 minus 1 is 0, and denominator it is here 2 pi I by z. If z tends to 1, so exponential of 2 pi I, it is also exponential of 2 pi I is 1, and 1 minus 1 it is also 0. That means our function gives 0 by 0 form. Now apply L'Hospital rule to find out whether next limit exists or not. In L'Hospital rule, we apply differentiation at numerator as well differentiation of denominator. So differentiate numerator with respect to z, so it gives us z minus 1. Minus 1 it becomes 0, and differentiation of z it is only 1. Okay, now denominator here exponential of 2 pi I by z, so e raised to z has derivative e raised to z itself, which multiplied by derivative of 2 pi I by z, which is a 2 pi I remain same, it is constant, and 1 upon z has derivative minus 1 upon z square, and minus 1 differentiation it comes 0. Now apply the limit as z tends to 1 gives 1 upon 1 multiplied by minus 2 pi I divided by 1 square, so it is finally comes minus 1 upon 2 pi I, which is finite and exists. Now here first we apply a direct limit, it comes 0 by 0 form, then after of it we apply L'Hospital rule, and by using L'Hospital rule we got the value for our function which is a minus 1 upon 2 pi I, which is a finite and exists. That means our option number B, it says that f has removable singularity at z which is equal to 1, it is true. So option C and D it is here, f has infinitely many poles, and D, each pole of f is of order 1. So as we solve in option first, we know that z which is equal to 1 upon n is a pole of f of z, and for every different value of a n, f of z has infinitely many poles, that is 1 upon n, and n gives infinitely many poles for our function. So option C, f has infinitely many poles, which is correct. Now go for next option D, each pole of f of order 1. So we need to check whether our function is having simple pole or multiple pole. If it is simple pole, that means it is having order 1. If it has order more than 1 like 2, 3, then it comes as a multiple pole. Here for finding pole, for a simple pole or multiple pole, we use for simple pole limit z tends to z naught, z minus z naught raised to m into g of z. Now substitute the value for g of z and at the point z naught where function is having pole. Now here put m which is equal to 1, so value of m it comes 1, and the pole we know that here 1 upon n is our pole of our function, so z minus z naught, that means z naught it is a 1 by n, and g of z, substitute the value for g of z which is given in our example, we consider it is the f of z. So here the multiplication of these two brackets, z minus 1 by n multiplied by z minus 1, it is here, and denominator it remain same. So if we substitute z tends to 1 by n, so z tends to 1 by n, it gives numerator as 0 and denominator it is also 0, so that means it comes again 0 by 0 form. So we know that when form it comes 0 by 0, then apply L'Hospital rule. So by L'Hospital rule, limit z tends to 1 by n, differentiation of a numerator divided by differentiation of denominator. So differentiation of a numerator it is here, and differentiation of a denominator it is here. Now substitute directly the value for z tends to 1 by n. So after solving these steps, we get 2 by n minus 1 by n upon denominator, differentiation of denominator. So after calculation, which gives 1 upon n minus 1 divided by minus 2 pi I into n square. So we can see that which is exist and a finite different solutions, which gives f has infinitely many poles and each pole is of order 1, that means simple pole. So our option C and option D both are true. In our example, we got the option number B, option number C and option number D. 3 options are true and option number A which is false. Thank you everyone.